Hello, analysis students. So this is continuing on the sequence of videos that I've been putting out with the aim of giving you walkthroughs for those homeworks that I, now can't collect. So, the goal of this group work, which you've gone through, you did it, is to prove the nested intervals theorem and to prove the fact that the real numbers form an uncountable set. And, well, let's first lead into the nested intervals theorem. So, the nested intervals theorem is about nested closed intervals. So let's start with this. For any real numbers a less than b, the closed interval from a to b, defined by bracket a, comma, b, close bracket, is the set of all numbers x, which satisfy that a is less than or equal to x is less than or equal to b. Right, that's all, and that's exactly what you knew it was. Similarly, the open interval is defined, the set of all x values, such that a is less than x is less than b. And we are going to start with the following lemma, just as a warm-up. I'm going to prove that 0 is in the infinite intersection of all of the intervals that look like 0, 1 over k. And let me remind you what the infinite intersection even means. If I give you a bunch of sets, a1, a2, a3, a4, indexed by natural numbers, so there's a first one, a second one, a third one, but they're all sets, then the intersection of all of these ak's is the set of all numbers a, such that for every natural number n, a is in the nth one of these sets. And that's exactly what it should mean. Right? What does it mean to be in all of the sets? Well, it means you should be in each of them individually. So let's prove that lemma. Proof. Let me pause for a second. I think a cat's eating plastic. No, there was no such problem. The cat was just walking on the strips of paper that we have for the cats to make fun noises on. Anyway, so let's do it. I want to prove that 0 is in that infinite intersection. So let's even just start with a sketch of what this means we'll need to show. So I want to show 0 is in the infinite intersection from k equals 1 on to infinity, the interval from 0 to 1 over k. And let's just translate that around. That's the same thing as saying, what does it mean to be in the infinite intersection? I want to show 0 is in the infinite intersection. There's the definition of the infinite intersection right above. That means I need to show this for a equal to 0. So I need to show that for every n in n, 0 is in the interval from 0 to 1 over n. That is, I need to show that for every natural number n, what's the definition of that closed bounded interval? I need to show that 0, this 0, is less than or equal to 0, that 0 is less than or equal to 1 over n. Oh, but that's like obviously true, right? It's just a matter of noticing that. So now we can compose the proof. By just manipulating what it is that we need to prove, we see it's obvious. So I need to prove something is true for every natural number n. So let's let k be in n. Every natural number k, right? Not every natural number n. This is phrased in terms of n over here. I don't like that. Let k be in n as k is bigger than 0, 0 is less than 1 over k. So as 0 is less than or equal to 0, is less than or equal to, in fact it's strictly less than, but I don't care, 1 over k, 0 is in 0, 1 over k. And let's just go ahead and notice this is true, because we proved it's true, for every k in the natural numbers, as we have shown that 0 is in the interval from 0 to 1 over k for all k in the natural numbers, we can make a conclusion. 0 is in the intersection from k equal to 1 to infinity of the closed interval from 0 to 1 over k. So I've got a cat attacking my pen. That's, in general, I'm always illegible, but that's why that particular bit turned illegible. Nice. So here's a particular conclusion to notice. The infinite intersection of all the intervals from 0 to 1 over k is not empty. That is not true if you use the open interval from 0 to 1 over k. What does the nested intervals theorem? It says whenever you take a bunch of closed intervals and intersect them all up, then as long as they're nested, their infinite intersection is non-empty. Cool. So, definition. A sequence of intervals, I1, I2, I3, is called nested if, oh, that's right, that typo apparently did not actually get fixed, if IN is the bigger one. So IN plus 1 is contained in IN now for every natural number n. I've got a cat scratching my face for attention. Well, the nested intervals theorem says that if you take a sequence of nested closed intervals, then even though they can get progressively smaller, right, they do get progressively smaller, that's what this line right here means. That says that they're getting smaller. Okay, well, let's... All right, well, continuing. The cat will interrupt again. He looks like he's about to. So the nested intervals theorem says, suppose that if I1 contains I2 contains I3, so that they're getting smaller as they progress, is a sequence of nested closed intervals, then the infinite intersection is non-empty. So let us prove. So let's write down the supposition. Suppose that I1 contains I2 contains I3 is a sequence of nested closed intervals. Since the nth one of them, IN, is a closed interval, that means that IN is the closed interval from AN to BN for some choice of AN less than BN. I need to show that the infinite intersection is non-empty, so I need to come up with something that should be in it. And here's the idea. I claim that the sequence AN and the sequence BN both converge. The limit of these things, I claim, is in the infinite intersection. In fact, we could describe exactly what the infinite intersection is, but we don't need to. We just need it to be non-empty. So let's do this. So consider any natural number n. I'm going to try to show that an is less than or equal to an plus 1 is less than bn plus 1 is less than or equal to bn. So I guess we'll start with this. As I n plus 1 is a n plus 1 comma b n plus 1 is a interval. Part of the definition of an interval is that the endpoints aren't equal. It automatically follows that an plus 1 is strictly less than bn plus 1. So there's one of the inequalities. Let's try to get the other two. So let's do. Now, an plus 1 is in in plus 1, which is a subset of in. Thus, an plus 1 is in in, which is the interval an to bn. So, by the definition of the open interval, an less than or equal to an plus 1 less than or equal to bn. That gives us another one of the inequalities we need. And maybe I'll even just do this similarly. an is less than or equal to bn plus 1 less than or equal to bn. And let's just in WOD see if we believe that it is similarly true. Is bn plus 1 in in plus 1? Yeah, it's the rightmost endpoint of in plus 1. Is in plus 1 a subset of in? It is. So that means that bn plus 1 is in in, and then all the same WODs walk. Putting this all together, we conclude that an less than or equal to an plus 1 less than or equal to bn plus 1 less than or equal to bn, which is all we needed. Secondly, explain why an is an increasing sequence and bn is a decreasing sequence. Well, by 1, for all n in n, an is less than or equal to an plus 1, and bn plus 1 is less than or equal to bn. Thus, an is increasing, and bn is decreasing. Cool. And that's good enough, right? Explain why 1 implies that b1 is an upper bound on the sequence an and a1 is a lower bound on the sequence bn. As I do with a lot of these, let's target just one of them. Let's show that b1 is an upper bound on the sequence an. So let's consider any n in n. So one of the things that is observed in 1 is that an is less than or equal to bn. As bn is decreasing, and n is greater than or equal to 1, it must be that bn is less than or equal to b1. Thus, an is less than or equal to b1, and b1 is an upper bound on the sequence an. Use monotone convergence to deduce the existence of the limits of these sequences. Let's see, an is increasing. Maybe I should say this similarly. a1 is a lower bound on bn. An is increasing, so an converges, increasing, and that's not enough. And bounded above, so an converges. Similarly, bn converges. If a and b are the limits of an and bn respectively, which exist because these sequences converge, let's prove that this inequality holds. So each inequality I claim might require separate arguments. Go through and do it. So let's see, what do I know? I know that I think this might not be enough space. So let's see. For all n in n, I know that an is less than or equal to bn. By limit laws then, the limit of an is less than or equal to the limit of bn. So I know that this inequality is actually strict, but taking the limit of a strict inequality gives a loose inequality anyway, so this is just fine. Thus, a is less than or equal to b. Cool. Next, I just need to see how an compares with a and bn compares with b. There are a few ways to go about this, but maybe I'll use this mindset. So let's consider any n in n. In fact, no, let's go with this argument. So monotone convergence does more than just say that an converges. So by monotone convergence, a is equal to the supremum of the set of all the things that look like an, where n is in n. Thus, a is an upper bound on the sequence an, and what does that mean? That means for all n in n, an less than or equal to a. Similarly, b is less than or equal to bn for all n in n. Putting all this together, thus, for all n in n, an less than or equal to a, less than or equal to b, less than or equal to bn. Explain why a and b are each in the interval, infinite intersection of the intervals of all of these INs. Well, let's do it. So let's see, by 5, for all n in n, an less than or equal to a, less than or equal to b, less than or equal to bn. Oh, cool, but thus, for all n in n, a and b are both in the interval from an to bn, which is exactly what in is. So that means for all n in n, a and b are both in in. That's exactly what it means to be in the infinite intersection. Since we found some things in the infinite intersection is not empty. That's what it means to not be empty. There's a thing in it. Thus, the infinite intersection from I equals 1 to infinity of n equals 1 to infinity of in is not empty. Cool. So, that is the proof of the nested intervals theorem. It seems like a technical thing, but that's a really important result, telling you something about the topology of the real numbers. Nice. So, the next topic that is in this is the uncountability of the reals. So let's prove that the reals are not countable. So we're going to prove this. There does not exist a surjection from the natural numbers to the reals. In terms of cardinality from set theory, that means that the real numbers are uncountably infinite. they're not in bijection with the natural numbers. So in order to prove that theorem, I need to show that every map from the natural numbers to the reals is not a surjection. What does it mean to not be a surjection? Well, it means that there is something in the reals that this function does not hit. And well, let's do it. Let f from n to r be any function. I need to find a real number not in the image of f. And the way I'll do it is I'll do it by using the nested intervals theorem. So let's make it happen. I will do so by defining some sequences via recursion. And you should think of these as endpoints of intervals, and these intervals are going to exclude more and more of the image of the function f. They'll be nested in intervals, so their infinite intersection won't be empty. Each one excludes more and more of the function, the image of the function, and so the thing that's in the infinite intersection won't be hit by that function. So there's the idea. Let's make it happen. So here we go. So here are some sequences. I will define a1 to be f of 1 plus 1, b1 to be f of 1 plus 2. So I'm going to go off to the side here. So that means that if there's f of 1, then here is a1, and here is b1. And the thing to notice is it sure looks like f of 1 is not in a1, b1. So the next step is to define a sequence by a recurrence relation. I want f of n plus 1 to not be in the interval from an plus 1 to the interval to bn plus 1. So let's try to motivate how to do that. There's more than one way to, of course. So let's see, if there's an and there's bn, then there are a few cases. Maybe your f of n plus 1 is over there. In that case, it sure looks like you could use the exact same a and the exact same b, and you would exclude f of n plus 1. And that is exactly reflected. It could be that f of n plus 1 is an. Oh, sorry. Well, no, this is fine. In that case, well, here's one option. There's a smaller interval which excludes f of n plus 1. Just take the midpoint and take bn. It could be that... Oh, that's bad. That's not so bad. But suppose there were f of n plus 1. In that case, what could you do? You could take that interval. And I guess the final case is, what if you made it all the way out there, f of n plus 1, weren't in the interval at all? Well then, again, you could use just the interval from an to bn. So, with that out of the way, here's the case-wise definition that comes from that. An plus 1 will be defined to be exactly an if f of n plus 1 is not equal to an. It will be the midpoint between an and bn if f of n plus 1 is equal to an. Bn plus 1 will be defined by bn if f of n plus 1 is strictly less than an, or if f of n plus 1 is bigger than bn. If f of n plus 1 is in between an and bn, then bn plus 1 will be the midpoint between an and f of n plus 1, and maybe just in order to emphasize this is the case, that is highlighted by this one. All right, so let's come up with that proof. So first, let's show that the interval from an to bn is actually an interval. Right? You need to for resolve the fact that an is less than bn. And, well, let's do it. We'll proceed by induction. Let's let n equal to 1. Then a sub n, well, is a sub 1. Oh, sorry, you can't see where I point. There. There's the instruction that tells you what a sub 1 is. There's the instruction that tells you what b sub 1 is, or in the case n equals 1. There, I think that will be better. Well, let's do it. So a sub n is exactly f of n plus, no, f of 1 plus 1. B sub n is equal to f of 1 plus 2. I want an to be less than bn. Well, it obviously is. Oh, hi, Oreo. Meow. Because 1 is less than 2, f of 1 plus 1 is less than f of 1 plus 2, so a1 is less than b1, as we claimed. Inductive step. Let's consider any natural number n, and assume inductively that an is less than bn. I need to show that an plus 1 is less than bn plus 1. Well, there's going to be a bunch of cases, so let's see what the argument will be. So I'm going to take a moment and even just write, it'll take a moment, I'm just going to, well, you know what, I'm going to take a moment and copy down the statement, the definition of the sequence, the occurrence definition, on the next page so I can reference it, because I have a terrible memory. I'll be back. All right, we're back. Nothing that bad happened. All right, we are back. So I've just copied down the definition of the sequences with, I mean, the middle case for bn was highlighted in lime green, so I've copied that down. So let's just go through the cases. Let's suppose that f of n plus 1 is less than an. Then an plus 1 is, well, look at the case, it's less than an. So f of n plus 1 is not equal to an, so an plus 1 is exactly the same as an. And bn plus 1 is exactly the same as bn in this case. I need to explain why an plus 1 is less than bn plus 1. Let's see. By the inductive assumption, an is less than bn, so as, well, I don't need to beat a dead horse on this one. So an plus 1, because it's equal to an, is less than bn, is equal to bn plus 1. Thus, the thing I care about is true. an plus 1 is less than bn plus 1, as we needed. The next case, let's suppose that f of n plus 1 is exactly equal to an. Then an plus 1 is equal to an plus bn over 2. Well, bn plus 1 is exactly the same as bn. Let's explain why an plus 1 is less than bn plus 1. Well, an plus 1 is exactly equal to an plus bn over 2, which is less than an plus, bn, which is strictly less than bn plus bn over 2 equal to bn. Well, what did I use in the middle step? I used that an is less than bn by the inductive assumption. And that's all I needed. Equal to. So since bn equals bn plus 1, we conclude an plus 1 is less than bn plus 1. And we're done. In the case that an is less than fn plus 1 is less than bn, then an plus 1 is an. Well, bn plus 1, look up, is an plus f of n plus 1 over 2. Should have zoomed in to write smaller. All right, well, let's try to do it. This time, let's start by thinking about bn plus 1, because that's the thing that's complicated. Let's see, bn plus 1 right now is set to be an plus f of n plus 1 all over 2. I would like to compare that with a sub n plus 1, which is, if you look here, is the same as an. So let's try to compare that with a sub n. Let's see, that is less than an plus an over 2, which is a sub n, where what did I use here? I used the fact that an is less, that inequality goes the wrong way. And I use there that an is less than f of n plus 1. By which case, I mean. So let's see. As an plus 1 is equal to an in this case, we conclude that bn plus 1 is bigger than an plus 1 as desired. Next case, let's suppose that f of n plus 1 is equal to bn. So let's scroll up. So that puts me still in this case. Still in this case. Oh, so in fact, you know what? That could be less than or equal to, and this case is suddenly redundant. Finally, let's suppose that f of n plus 1 is bigger than bn. Then in this case, an plus 1 is equal to an, bn plus 1 is equal to bn. Let's complete the proof, and this is, well, an plus 1 equals an, which by the inductive assumption is less than bn, equals bn plus 1 in this case. Thus, an plus 1 is less than bn plus 1. So none of those cases were particularly complicated, but you kind of need each of them. Cool. So in each of those cases, which are all the cases, we get an plus 1 is less than bn plus 1. That completes the inductive step. So we have now proven, using the principle of mathematical induction, that an is less than bn for every natural number n. I'm going to pause for a second and take a breath. Okay, I'm back. So, the next item that needs to be checked is that, right, so all of these are actual intervals. Let's check that these sequences, the intervals defined by them, these are endpoints of an interval. Let's check that it's actually a sequence of nested intervals. So what do I need to check? I need to check that an is increasing, bn is decreasing. Then I'll have that these intervals will be nested. So let's do that. So suppose that f of n plus 1 sorry. Let's consider any n in n. We want to show these two inequalities are true. Well, the first case is like the silly case, the easy case. f of n plus 1 is less than an, then an plus 1 is equal to an. Bn plus 1 is equal to bn. Well, then as an plus 1 equals an, we certainly have an plus 1 less than or equal to an. Similarly, we have bn plus 1 less than or equal to bn. Oh, well, we do have this, but this is not what we want. We need an less than or equal to an plus 1. But since they're equal, that's true too. Suppose that f of n plus 1 is equal to an. In that case, an plus 1 is the midpoint between an and bn. Well, bn plus 1 is exactly bn. So let's do it. Let's see, bn plus 1 is less than or equal to bn holds automatically. As bn equals bn plus 1. So that's like easy. Now I just need to check the other one. So let's look at an plus 1 because that is the bit that looks complicated. Let's see, an plus 1 is equal to an plus bn all over 2. And I need to try to figure out how to compare that with an. So the only thing I see on the right-hand side of this, which isn't an, is that bn. So let's think about that bn. Let's see, so this is bigger than or equal to an plus an over 2, since bn is bigger than or equal to an, which is equal to an. That completes the proof. The next case is that an is less than f of n plus 1 is, and I'm going to stick with that, it's really more natural to have that less than or equal to right there. Oh, good. Someone turned in a thing. Well, in this case, an plus 1 stays the same. bn plus 1 becomes the midpoint between an and f of n plus 1. And, well, one of the inequalities that we need to show is obvious, as, well, let's see, an plus 1. No, write down the thing that is actually the thing that we want to show. An less than or equal to an plus 1 is automatic. Well, I don't like that water. It holds automatically. Let's say this. It is a truism, as an plus 1 is equal to an in this particular case. To get the second one, well, let's take the more complicated side. bn plus 1 is equal to an plus f of n plus 1 all over 2. Now let's see, that's less than bn plus f of n plus 1 all over 2 because an is less than bn. F of n plus 1 is less than or equal to bn, so this is less than or equal to bn plus bn all over 2, which is, of course, just bn. And let's write down what we used. Because an less than or equal to bn and f of n plus 1 less than or equal to bn. Cool, so that does it. Just as before, for this case is now redundant. And we're left with the remaining case is also a super easy one. Where is it? I just inserted the page. Sorry. All right, we're back. Oh, good cat. So the final case is f of n plus 1 is strictly greater than bn. In that case, an plus 1 is the same as, an. Bn plus 1 is the same as bn. And maybe I'll see case 1 above, because it's exactly the same setup, right? Thus, in each of the cases, we get an is less than an plus 1, and bn plus 1 is less than bn, which is all we needed. That completes the proof. All right, well, so I now see a bunch of intervals, and it's really easy to see that they're nested. So let's see that they're nested. Let's show that for every natural number n, an plus 1 comma bn plus 1 is contained in the interval from an to bn. Well, let's do it. Let's consider any x in an plus 1 comma bn plus 1. Then, what do we know? I know that an plus 1 is less than or equal to x is less than or equal to bn plus 1. That's what it means to be in the interval from an plus 1 to bn plus 1. I need to get the same thing as true with an's and bn's. So let's see, by the preceding lemma, which hopefully is lemma 2.5.6, by lemma 2.5.6, I know that an is less than an plus 1. And I also know bn plus 1 is less than bn. Putting this together, what do we see? We see that an is less than or equal to an plus 1, less than or equal to x, less than or equal to bn plus 1, less than or equal to bn, as an is less than or equal to x is less than or equal to bn, x is in an comma bn. And so let's just write down what we proved. We considered any x in the interval from an plus 1 to bn plus 1. So we consider any x in the interval from an plus 1 to bn plus 1. So we get something for every x in an plus 1 to bn plus 1. What did we show? We showed that x is in an comma bn. So x is in an comma bn. Since we've shown that everything in this interval is also in that interval, we get the containment we wanted. Nice. It was clear from the pictures we drew that f of n is never in the interval from an to bn. Let's prove that. Let us show that for every natural number k, f of k is not in ak comma bk, where an and bn are the sequences described above. So this might look a little bit like an inductive argument in that I'm going to have the case k equals 1 as a first case, but the thing that looks like an inductive step isn't actually inductive. I just need to do two separate cases because a1 and b1 are defined differently from the rest of the terms of the sequence, so I'll need a different argument when k is equal to 1. When k is equal to 1, we have a1 equal to f of 1 plus 1, and b1 equal to f of 1 plus 2. Well, let's explain why. Well, let's see. It's obvious why, right? As f of 1 is less than f of 1 plus 1 equals a1, f of 1 is not in a1 comma b1. It didn't even matter what b1 was defined to be. Thus, the claim holds at least when k equals 1. That's not much of a result, but it's, important to prove everything. All right, so let's prove it now when k is bigger than 1. Well, when k is bigger than 1, then I can write k as n plus 1, where n is a natural number. The natural number is n equal to k minus 1, but that doesn't matter. There are 5 cases. Let's suppose that f of k, which is f of n plus 1, is less than an. Then in this case, an plus 1 is an. Bn plus 1 is exactly bn. And let's go through the argument. Let's see. Because f of n plus 1 is less than an, which is equal to an plus 1, I conclude that f of n plus 1, which is equal to f of k equals f of n plus 1, is not in an plus 1 comma bn plus 1, which is ak comma bk. So we get the desired result. F of k is not in the interval from ak to bk. Did I skip a case? Oh, I did. So that's page 6. And now there's just a bunch of other cases that are all really similar. Skip a case. Wait, no, there's something deeper wrong here. 68. This is also page 68. Okay. Hold off for a second. There we go. That looks more reasonable. All right, there's just another ton of cases. So let's suppose that f of n plus 1 is equal to a sub n. In that case, a sub n plus 1. I think I'm not going to go through all the cases. All right, you'll get the point. A sub n plus 1 is an plus bn over 2. Bn plus 1 is exactly bn. There's the thing that I need to prove. Well, let's maybe even just draw a picture. Oops, hi Huxley. The dog is trying to pull the tablet off of the table. Let's draw a picture of this situation. So there's an, there's bn. I'm in the case that this right here is f of n plus 1. And I'm going to take the interval from the midpoint to bn. Okay, well, I can see why it's not in the interval. It's not in the interval because f of n plus 1 is less than the new an. So let's just explain that. Let's see, f of k is equal to, well, this is the wrong way to do it, I think. Let's see, a sub n plus 1 is equal to a sub n plus b sub n all over 2. I need to compare that with f of n plus 1. So f of n plus 1 is just a sub n. So let's try to turn this thing into something that just has a sub n. So this is bigger than an plus an over 2, as an is less than bn. But this is exactly an, which is equal to f of n plus 1 by our current case. And now let's just put the conclusion. Thus, thus, as f of n plus 1 is less than a n plus 1, f of k, which is equal to f of n plus 1, is not in the interval from a n plus 1 to b n plus 1, as we desired. Well, maybe I should be more explicit, equal to ak, comma, bk, which is what we wanted. F of k is not in the interval from ak to bk. And the rest of the cases are almost exactly the same. Cool. So I'm going to skip. All right, so with that proof done, you just have to write down the remaining cases. We'll already construct an element that's not in the image of f. So here, let's do it. So we've checked that this is a sequence of nested intervals. The nested intervals theorem concludes that this infinite intersection of nested closed intervals is not empty. So there exists something in it. There's the something. This is the thing. This element. I will show that this element is not in the image of f. So let's do that. So let's consider any natural number k. Well, by assumption, k is in the infinite intersection of all of the an's. So that means that this y is in fact in every single one of the ak, comma, bk's. On the other hand, we've checked that f of k is not in the interval from ak, comma, bk. Why does this mean that y is not equal to f of k? Well, if y were equal to f of k, then y would be in the interval from ak to bk. But because y would be equal to f of k, y would not be in the interval from ak to bk. This is a contradiction. Thus, y is not equal to f of k. So what have we done? I've constructed a number y such that for every natural number k, y is not equal to f of k. That means that this y is not in the image of f, and so f is not surjective. This completes the proof. Cool. Let's stop.